Lens is long. Lens is long. Lesson 21. Okay, yes. This lesson sucks to do on video because you just got to see this. Here, I don't know if you can see any of this or not, but here's a little demonstration of Lenz's law. So this is, there we go. This is a ball bearing. It is not magnetic. It's not a magnet. And this is a metal pipe, and then there's a glass pipe here. I'm just going to put it through the metal pipe, and so I'm not sure what you can see, but oh no, 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 no. That was the wrong one. That one was the magnetic one. Here we go. Here's the non-magnetic one. So I'm just going to drop it through the pipe, and it just goes right through. Ooh, I'm pretty fast. There we go. It just goes right through. Hey, can anybody see that? I don't know if you can or not. If you can't, just watch the video. It goes right through. Okay, but now I take a magnet. Be careful. Now I take a magnet. This one's magnetized, and I drop it through. And you can see it takes forever to go through. Now, what you can't see, and what I want you to see is you look down there. The ball is not touching the sides at all. People think, oh, it's just magnetized to the side, and it's just therefore it's slowing down. If you look down it, you can totally see that it's not touching the sides at all. So what's causing that? Why is it going so slow through the pipe now? And if you get a long pipe, it takes forever to go through. And there's a good lab related to this one. You can do this all day. Oops. Okay. So what's causing that? Well, we learned in the last lesson that a changing magnetic field induces a current. So a changing or a moving magnetic field, so this magnet is moving, it's going down, so it's going to go through the pipe. So as it gets near this copper pipe, which copper is a very good conductor of electricity, as it gets near the copper pipe, it's going to induce a current in the pipe. So all of a sudden, this pipe has a current going around it because this magnet is inducing a current. Now we know from the first lesson that if you have a current in a solenoid, what does it do? It creates a straight magnetic field. And so you can probably guess what's happening here is that this changing magnetic field will induce a current around this pipe, and that current will itself induce a magnetic field that opposes the motion of the magnet. So if I'm dropping the north end of the magnet through this pipe, it will create a magnetic field. The induced current will create its own magnetic field going with the north end of that magnetic field facing up. So therefore, it's repelling it. So it's working against gravity and it's repelling it. And that's why it moves so slowly, because the magnetic force is actually pushing this thing up against gravity. And if I had a strong enough magnet or that pipe that was really conductive, I could probably drop that in and it would probably, at some point, it would just levitate because the magnetic force would be strong enough to counteract gravity completely. Okay, so let's just go through that again quickly. So the changing magnetic field induces a current in the pipe, and that induced current makes its own magnetic field that opposes the direction of motion of the magnet. Okay, and here's how Lenz's law works in your notes. Okay, so what do we got here? We got a, well, you can, let's actually let's do our own example here. So here's a pipe, and here's a magnet. Actually, let's do this vertically. So it's like the one we did just a second ago. So here's the pipe. You're going to drop a magnet through this pipe. Here's the magnet. And let's say that this is the south end and this is the north end of the pipe. And the question is going to be, what is the direction of the electron flow around this pipe? Okay, so if you're dropping this magnet into this pipe here, what's going to happen? What kind of magnetic field is going to be created within this pipe? Well, it's going to, as it goes into the pipe, a south pole must be created here. A south pole must be created there to repel so that they repel, and therefore this magnet is getting pushed up by this force and pulled down by gravity. So that must be a south pole there. And if that's the south pole, then which way will the electrons flow? Right, your thumb points towards the, we're back into the second hand rule, your thumb points towards the north end of the magnet, So if that's the south pole there and the north pole down here, then which way are the electrons going to go? They are going to go this way. So let's say if I just make that into a solenoid. There, that's the direction of the electron flow. Okay, now the interesting thing is what happens when the magnet comes out at the bottom. When it comes out at the bottom, let's just erase that. Then, assuming this magnet is the same as the north and the south here, now at the bottom, the polarity of the magnets, in other words, the north and south, are going to have to reverse, right? Because now you want an attractive force here. So you want a south pole here so that this south and this north attract each other because it's at the bottom now. And you want it to be slowing down. If this was north, again, if this was north right here, then they would be repelling, and all of a sudden that thing would be pushed down faster than gravity. So at that point, it shifts, and now the direction of the electron flow shifts and becomes the opposite. Okay, so that's basically Lenz's law. I think that's a pretty good example. You got a couple of examples in your notes there. Watch some video on Lenz's law. It's a really fascinating concept, and it's good in relating it to work and energy. Clearly, if they were reversed, if this was a north pole here, then I would be getting free work. I'd be getting work for nothing. And so what happens is this produces a resistance. And if you get a generator, one of those generators where you turn something and it lights up a light bulb, the faster you turn it, the more force there is. You have to use more force because you have to do work to get energy. So it's kind of it's in conjunction with the conservation of energy and the fact that to have energy, you must do work. So there's Lenz's law. I hope you got that. It's a great physics thing. And that ends magnetism, really. So if you've watched all these videos and you've done your notes, you should be around magnetism. You should have a good feel for it. You should be able to finish the assignment. And let's make the assignment due next week because we just need to finish magnetism before Easter break. And then when we get back after Easter break, we're going to pile through electromagnetic radiation. Okay, enough talking. And remember, if it's wrong, it can't be wrong. Right, Anthony? You better watch this video. That was just for you.